Welcome to The Explainer. Today, we're going to dive into a really clever piece of rocket engineering. I mean, it's almost a paradox, right? We're talking about a high-performance engine that powers itself using its own waste heat. How cool is that?
Okay, so let's start with a really basic problem in rocketry. If you want to generate a ton of thrust, you've got to shove massive amounts of super cold propellant into a combustion chamber that's already at, just insane pressures. To do that, you need some seriously powerful pumps. So here's the big question. What powers those pumps?
Well, the answer is it's like a form of engineering judo. See, normally, all that intense heat from the engine is a problem you have to manage. But with the expander cycle, nope. You turn that waste heat into the solution. It becomes the very thing that powers the engine's own machinery. It's this beautiful, closed-loop, self-sustaining system. All right, so how does this whole ingenious process actually work? Let's break it down and follow the fuel on its journey, step by step.
Okay, so here's a look at the entire system. And at first glance, it kind of just looks like a normal rocket engine. But the real magic, the clever part, it's all in the plumbing. We're going to follow the path of the fuel as it does two super important jobs at the exact same time.
So here's the journey. First up, you've got this super cold liquid fuel. Its first job is to act as a coolant. It runs through all these little channels in the nozzle to stop the whole thing from, melting. As it's doing that, it soaks up a ton of heat and instantly flashes into a high-pressure gas. Now this expanding gas gets sent over to spin a turbine. And what does that turbine do? It powers the pumps for both the fuel and the oxidizer. And then finally, after it's done all that hard work, that very same fuel gets shot into the combustion chamber to be burned for thrust. It's just a perfect loop. Absolutely nothing goes to waste.
But of course, like any brilliant engineering solution, this design has its limits. There's a fundamental physical law that gets in the way. You can't just keep making these things bigger and bigger forever.
And this is where some basic physics, the square-cube law, comes into play. Think about it. As you make the engine bigger, the surface area of the nozzle, that's the part providing the heat, it grows by the square. But the amount of fuel you need to heat up, that grows by the cube. So you pretty quickly get to a point where the engine is so massive that you just run out of nozzle area to boil enough fuel to power the pumps. The system just can't feed itself anymore.
This law basically puts a hard ceiling on how much thrust a standard expander cycle engine can make. The cap is right around 3,000 kilonewtons. And don't get me wrong, that is a lot of power, but it does mean these engines generally aren't the right fit for, say, the giant first stage of a heavy-lift rocket.
But engineers, they're a clever bunch. Of course, they found a way to push past that limit, even if it meant making a little trade-off.
And here's how they did it. So on the left, you see the closed cycle we've been talking about. But look over on the right. See that little pipe coming off the turbine? That little guy is the key. That's what makes it an expander bleed cycle. So what's happening here is they're bleeding off a little bit of that gas after it's already done its job spinning the turbine. By venting it, they get rid of a ton of back pressure. That's the force that's kind of pushing back on the turbine blades. With that pressure gone, the turbine can spin way faster. That means it drives the pumps harder, which means you can cram more propellant into the combustion chamber. The trade-off? You lose a tiny bit of efficiency, but what you gain is a huge boost in total thrust.
So you might be asking, why go through all this trouble? Why is this cycle, with this built-in limit, so popular? Well, it's because the expander cycle has some really big advantages.
The benefits are huge. For one, the gas that hits the turbine is actually pretty cool, almost room temperature. That means there's way less stress on the parts, which is just fantastic for reusability. The whole design is also super robust. And, this is a big one, it's inherently safe. We'll talk more about that in a sec. And on top of all that, the design is perfect for getting incredible performance in the vacuum of space, just squeezing out every last bit of thrust. There's a great story about the legendary RL-10 engine, which is a total expander cycle workhorse. It shows just how tough this design is. During testing, the engineers literally fed loose insulation foam into the fuel line on purpose. Now, a more complicated engine, that could have been a disaster, an explosion maybe. But the RL-10, with its nice wide channels, it just chewed the foam up and spit it right out. No problem at all.
And this brings us to what might be the most elegant part of the whole thing. Remember that square-cube law? The thing that limits the engine's power? Well, it also acts like a built-in safety switch. Other engine designs can sometimes spiral out of control into a catastrophic failure. But an expander engine, it's physically impossible for it to run away with itself. So its biggest limitation is also, in a way, its greatest strength.
And hey, this isn't just some theory on a whiteboard.
These engines are the real deal. Proven, flight-tested workhorses that have been exploring space for decades.
So if you look at the classic, super efficient expander cycle, you see it powering these iconic upper stage engines like the RL10 and Europe's Vinci. But when you need more muscle, designers switch to the expander bleed cycle. And you can see that massive jump in thrust with engines like Blue Origin's BE3U and Japan's powerhouse, the LE9. It's a perfect illustration of that trade-off. Do you want maximum efficiency or do you want raw power?
So at the end of the day, the expander cycle, in both its forms, is just an incredibly reliable, safe, and efficient design. And that really makes it the perfect choice for the upper stages of rockets. You know, the ones that have to do complex missions and reliably restart way out there in deep space.
So with its incredible mix of safety and efficiency, you have to wonder, could this elegant cycle be the real workhorse for our future in deep space? It's just one of those designs that proves that sometimes the most brilliant solution is the one that's clever enough to just power itself.